Okay, here we are in section 3 of chapter 7, still dealing with, of course, factoring. So far, I'm going to recommend that you go through, once again, the now 5 steps to factoring. First, make sure that the polynomial is in descending order of powers. You want to make sure, of course, in step 2, that you have a positive leading coefficient. Moving on to step 3, you're going to check to see if there's, first of all, a greatest common factor to factor out. And that could be, of course, the form of a constant variable, monomial, or polynomial. Should you have a 4-term polynomial, that's when you factor by grouping. And lastly, we talked about section 7.2, the trinomials, the 3-term polynomials, that there were two different types, I should say. The first type was of x squared plus bx plus c. Those were the easier kind, okay, because your leading coefficient was simply 1. If you have a different leading coefficient, any other leading coefficient other than the number 1, that was a little bit more difficult, but what I showed you, remember, was that borrow and give back method where you kind of trick the trinomial into the easier kind temporarily to form a simpler polynomial to factor, okay? The last type of factoring that we're going to explore in section 7.3 is what happens when we want to factor some special binomials. Okay, well, trinomials are 3 terms. Binomials are going to be special polynomials that have just 2 terms. Now, once again, that does not say that you should overlook the earlier steps. Steps 1, 2, and 3 are very important. Step 4 only deals with 4-term polynomials. Step 5 deals with only 3-term polynomials. And step 6 is going to deal with exclusively 2-term polynomials. Okay? And there are going to be 2 different types that we're going to take a look at. We're going to take a look at perfect squares, and we're going to take a look at perfect cubes. Now, what's meant, first of all, by a perfect square number? Okay, let's take a look at some examples of numbers that are perfect squares. Now, what's meant by a perfect square number is a number that you get when you square another number. So think about numbers, and when you square it, multiply it by itself, you get a number. That number that you get is a perfect square number. We can classify it like that. So a perfect square numbers, I'm going to give you some examples, okay, because any number when you square it will form a perfect square number. Well, here are some very common ones. 1, 4, 9, 16, 25, 36, 49, 64. Some other numbers that are perfect square numbers. 81, 100, 121, 144, 169, 196, and I'm going to stop at 225. These are very commonly found perfect square numbers in problems. How do we get them? We take another number and square it. For example, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared, of course, is 16, and so on. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and finally 15 squared. Okay? These 15 numbers are the numbers that you get when you take the numbers 1 through 15 and square them. Okay? We also have perfect square variables. Okay? If a number can be squared to form another number, a variable can also be squared to form another variable. And here is also a list of perfect square variables. X squared, that's a perfect square variable. How do we get it? We take x and square it. If I take x squared and square it, you get x to the fourth. If I take x cubed and square it, you would get x to the sixth. X to the eighth is another one. And then, of course, x to the 10th. There are plenty of others. For example, I could have x to the 22nd. I could have x to the 34th. I could have x to the 46th. I could have x to, let's say, the 58th. These are all examples of perfect square variables. I could have, let's say, further down the road, x to the 246th power. These are all examples of perfect square variables. And if you want to think of it, x to the n power would be considered a perfect square variable, provided n is an even number. As long as the exponent is an even number, x to the n would be considered a perfect square variable. Okay? And these are going to be very important to us not only here, but they will also become important to us later on in chapter 9 when we talk about radicals. Okay, so hold on to these lists of perfect square numbers and perfect square variables because they will come back to assist us when we talk about radicals, particularly square roots, in chapter 9. Now, what are we going to do with these perfect square numbers and perfect square variables in terms of factoring? Well, the first thing that we're going to take a look at is the difference, which of course means subtraction, of two perfect squares. Okay, now that we know what a perfect square variable and a perfect square number is, we're going to take a look at what happens when we have the difference or the subtraction of these two perfect quantities. For example, let's say we have x squared minus 9, and we want to factor this. Well, step 1 is done because it's in descending order. Step 2 is done, the leading coefficient is positive. Step 3, there's nothing common to factor out. It's not a 4 term, so we're not going to worry about grouping. It's not a trinomial, so we don't have to worry about factoring down the trinomial. What we have here is the difference of two perfect squares. And if I may, I'm just going to erase this for a moment. I'm going to give you a formula to follow. That if we have a squared, that's a perfect square, minus b squared, that is also a perfect square, that would factor down into an a plus b and an a minus b. That's the formula that we're going to follow when we look to factor down the difference of two perfect squares. Okay? Once again, a quantity squared minus a second quantity squared is going to equal a plus b times a minus b. So now let's take a look at that example once again. Excuse me. X squared minus 9. Okay? And so I'm going to set up my parentheses. Now we need to think about what would I have to multiply to form an x squared? Well, that of course is an x and an x. I know my signs according to the formula. One will be plus, the other will be minus. And then factors of 9. Okay, what would I have to square to get 9? That would give me my b value. And of course the answer, what would I have to square but the number 3? So x plus 3 times x minus 3 is the factored form. Can I factor this any further? No, I cannot. Let's do another example. Let's say we have 4x squared minus 81. Well, the number 4 is a perfect square. It's on the list. X squared is also a perfect square. It's on my list of numbers, variables rather. 81 is on my list of perfect square numbers. And since I'm subtracting, I once again have here the difference of two perfect squares. So I'm going to look to now factor this down. I'm going to set up my parentheses. Factors of the 4x squared would have to be 2x and 2x. According to the formula, I need to put one plus, the other minus. And what would I have to square to get 81 but the number 9? So I need a 9 and a 9. Remember, you can always check your factoring by multiplying these two quantities back together. And if you were to multiply these two polynomials, it would bring you back to the original. Okay? Let's take a look at another example. Let's say we had x to the 6th minus 25. We want to factor this. Okay? Is x to the 6th a perfect square variable? Well, yes, it is. Because based upon our definition, we said as long as your exponent is an even number, this would be classified as a perfect square variable. 25 is also a perfect square number. It's over here on my list. And since we are subtracting these, we can factor this further. And so I would break it down. Factors of x to the 6th. Okay, that of course would have to be x to the 3rd times x to the 3rd. I know I need one plus, the other minus. Factors of 25 would have to be 5 and 5. Okay, here we have once again the difference of two perfect squares. Let's try another one. Let's say we have a 36 x to the 8th minus, let's say, the number 25 y to the 4th. Once again, we want to factor this down. Factors of 36 have to be 6 and 6. Factors of x to the 8th, that's going to be x to the 4th and x to the 4th. I'm going to put a plus and a minus following my formula, one positive, the other negative. And now I have to do the same thing with the 25y to the 4th. Factors of 25 would be 5 and 5. Factors of y to the 4th power have to be y squared and y squared. And you can't factor that any further. Okay, you would stop there. Okay? Always look at each term. And you want to take a look at each term of your polynomial, and you want to make sure that it is in fact perfect squares. 36 is 6 squared. 25 is 5 squared. X to the 8th, that's an even power. Y to the 4th, an even power. Okay? Notice here how I get the terms in terms of my variables. Simply you have to divide the exponent by 2. Okay? 8 divided by 2, 4 and 4. 4 divided by 2, 2 and 2. And that is your fully factored form. Okay? Always look to factor completely. All right? Let's take a look at another one. X to the 4th minus 81. We want to factor this completely. Well, it is the difference of two perfect squares. So I'm going to set up my parentheses. Factors of x to the 4th. That, of course, would be x squared and x squared. I know one has to be plus, the other is minus. Factors of 81, 9 and 9. Now, believe it or not, this is not the final answer, because the directions will always read to factor completely. Factor as much as possible. And we can't stop here, because the polynomials, okay, we could still factor further. We can't factor the first part any further, x squared plus 9. That's not the difference of two perfect squares. But x squared minus 9, that should sound familiar. That was the very first problem that we did. Okay, so we have to factor this further. So I'm going to leave the x squared plus 9, and now I want to factor this further because it is still the difference of two perfect squares. The factors of x squared, x and x. Once again, plus and minus, and then the factors of 9 would have to be 3 and 3. So this is your fully factored form of the original polynomial. If I was to multiply these three terms together, it would take me back to the original. And you must factor completely. Now, you might be asking yourself, well, why can't I do anything with this x squared plus 9? Okay, well, that's because x squared plus 9, what we have here, is not the sum, it's not the difference of two perfect squares, but it is the sum of two perfect squares. And if you have the sum of two perfect squares, that's not factorable, okay? X squared plus 9, there is absolutely nothing that you can factor this down to give you an x squared plus 9. Same thing, let's take a look at if I had x to the 8th plus the number 16, okay? I agree, x to the 8th is a perfect square. 16 is also a perfect square, but because we are adding these, well, that's the sum of two perfect squares, and the sum of two perfect squares is prime. We cannot factor that down, okay? The difference of two perfect squares, we can factor that, but the sum of two perfect squares is prime, okay? What about this one? Let's say we have x to the 8th minus 1. We want to factor this as much as possible, okay? Well, we would start. X to the 8th, that's a perfect square. 1 is also a perfect square. And since we are subtracting them, we can factor this down. X to the 4th, x to the 4th, plus minus, and factors of 1, 1 and 1. But we're not done, okay? Although I can't do anything with x to the 4th plus 1, x to the 4th minus 1 is factorable because it's the difference of two perfect squares. So the x to the 4th plus 1 comes down, but now I'm going to factor down x to the 4th minus 1. Well, factors of x to the 4th, that of course would be x squared and x squared. I know I need to put one plus, the other minus. And factors of 1 will still be 1 and 1. Once again, you might think that you are done with this problem. However, I could still factor. I can't do anything with the first polynomial. I can't do anything with the second polynomial. However, this third polynomial is still the difference of two perfect squares. So the first term of x to the 4th plus 1 comes down. The second polynomial of x squared plus 1 also comes down. However, the x squared minus 1, I could factor that down. So I set up another two pairs of parentheses. Factors of x squared, x and x. I need different signs, plus and minus. And now the factors of 1 and 1 are still going to be 1 and 1. That is your fully factored form of the original polynomial. If I was to multiply these four expressions together, it would bring me all the way back to the original polynomial. That's why they are equivalent. What about this one? Let's say we have a 3x to the fourth minus 75. Now think carefully about this one, okay? Most people, when they look at this, they see, well, gee, it's subtraction. They see the x to the fourth, but the 3 and the 75, they think, well, gee, 3 is not a perfect square. 75 is also not a perfect square. So a lot of times people think that this is prime, okay? But those people have forgotten the earlier steps. Yes, step 1 is done. It is already in descending order. Step 2, the leading coefficient is positive. However, step 3, if you forgot about step 3, you'll get this problem wrong, because step 3 tells us that we need to factor out any greatest common factors. And in this particular problem, there is a greatest common factor, and it happens to be the constant 3. Remember, what do we do with greatest common factors? We take them, place it outside the parenthesis, and then you would have to divide each of these terms by the 3. Now we have 3x to the fourth divided by 3 is simply x to the fourth minus 75 divided by 3 is 25. And now we can see that we still have the difference of two perfect squares. So the 3 has to come down for the ride. And now I'm going to set up my parentheses. Factors of x to the fourth would be x squared, x squared. According to our formula, one will be plus, the other will be minus. And factors of 25 would have to be 5 and 5. Okay, now we have the fully factored form of the original polynomial. Can't factor this any further, okay? So that is the perfect squares, all right? The difference of two perfect squares is factorable. The sum of two perfect squares is not factorable, okay? So when dealing with perfect squares, let's just review this. When dealing with perfect squares, if you have a squared minus b squared, that's going to become a plus b and a minus b. If we have the sum a squared plus b squared, well, this is the sum of two perfect squares. That's not factorable. That is in what we call prime. Okay? All right. Now that's perfect squares. Now we have to talk about perfect cubes. Now perfect cubes we're going to handle in a similar way. First, I'm going to give you some perfect cube numbers. A much shorter list. I gave you 15 perfect squares to be familiar with. However, because the cubes grow so rapidly, I'm only going to give you 5. Well, the first number 1, when you cube it, you get 1. So 1 is a perfect cube. If we take 2 and cube it, you get the number 8. So 8 is a perfect cube. 3 cubed, 27. 4 cubed, 64. And 5 cubed is 125. So I'm only going to give you 5 perfect cube numbers to be familiar with. Do be careful, because the number 1 and the number 64 are also perfect squares. Okay, so you have to look at the problem in its entirety. All right, you have to make the determination, are those two numbers, 1 and 64, are those numbers acting as squares, or are those numbers acting like cubes? Now, variables can also have perfect cubes. So let's talk now about perfect cube variables. Now we said the perfect square variables had to be even numbers, which means in essence they had to be divisible by 2. Well, here are some perfect cubed variables. X to the third, x to the sixth, x to the ninth, x to the 12th, x to the 15th. Those are the first 5 perfect cubed variables. And of course there are others. X to the 18th, x to the 21st. I could go with x to the, let's say, 33rd. I could go with x to the 52nd. Okay? These are all examples of perfect cubed variables. Okay? Now, x to the n is going to be considered a perfect cubed variable provided n is divisible by 3. You'll notice, you'll take a look here at all of these exponents. They are all divisible by 3 evenly. Okay? Do be careful. Once again, some of them can also be considered perfect squares, like x to the 6th, x to the 12th, x to the 18th, even x to the 52nd. Okay? Because not only are they divisible by 3, but they are also divisible by 2. Actually, x to the 52nd, that's not correct. I was thinking 42nd. My apologies. X to the 42nd is also not only a perfect cube, but it is also a perfect square. Okay, because 42 is divisible by 3. All right. So, when we take a look at perfect cubes, once again, I'm going to give you a formula for the sum and difference of 2 perfect cubes. Okay? First of all, let me give you the formula for the sum of 2 perfect cubes. A to the third plus b to the third is going to equal a plus b times a squared minus ab plus b squared. That is the formula for the sum of 2 perfect cubes. Now, when it comes to the difference, there is a similar formula. If you have a cubed minus b cubed, that's going to equal a minus b times a squared plus ab plus b squared. That is the different formula that we will use when we talk about the difference of 2 perfect cubes. Okay? So whether or not you're talking about the sum, you will use one formula, or if we talk about the difference, we will use a different formula. And I think I spelled the word difference wrong. D-I-F-F-E-R-E-N-C-E. There it is. Did I spell it right up here? Yep, I did. Okay. That's why I teach math. Okay. So, whether we have the sum or difference of 2 perfect cubes, these are the formulas that we're going to follow. Now, you'll notice there's a lot of similarities to these 2 formulas. The one thing that is different are the signs. And to help you with the signs, I'm going to suggest that you might want to remember the word soap. The word soap may help you with the signs. When we talk about S, let's take a look here. When we're adding here. When we're subtracting, we subtract here. So for S, that stands for the same sign, okay? So, because A and B doesn't change without the formula. The formula stays the same with the A and the B. What changes are the signs. And the sign here is going to be the same as the initial sign. Let's take a look at that second sign. When I am adding the two cubes, when it comes to this sign, I subtract. When I am subtracting the two cubes, over here I have to add. So for this particular sign, it is the opposite of the original sign, okay? So same sign here, opposite sign here, okay? AP, that stands for always positive. Because regardless of whether or not I am adding or subtracting these perfect cubes, this last sign will always be a positive sign. So that's why students sometimes like to use that word SOAP, okay? Same, opposite, always positive, to help them remember the signs of the formula, because everything else stays the same. The A, the B, the A squared, the AB, and finally the B squared, okay? Let's take a look at some examples where we can use this formula for the sums and differences of two perfect cubes. For example, let's say we have x to the third plus the number 8. Well, x to the third is a perfect cube. It was on our list. It was the first one. And the number 8 is also a perfect cube because it's on our list, okay? What you want to think about, okay, what would I have to cube in order to get x to the third power? And of course, that would have to be the variable x. Plus, what would I have to cube to get the number 8? And of course, that would have to be the number 2. So now what this is, what's being demonstrated here, is a to the third plus b to the third is going to equal my formula of a plus b, a squared minus ab plus b squared. And wherever I see the x, or should I say wherever I see the a in my formula, I'm going to plug in an x. Wherever I see a b in my formula, I'm going to plug in the number 2. Okay? So, a plus b would now have x plus 2. Now I need to take a and square it. Well, if a is x, and if I square that, we would get x squared. Minus, now I have to take a times b. If I take a times b, that would give me a 2x. Plus, well, now I have to take b and square it. Well, 2 squared would be 4. And this would be your factored form of your polynomial. Let's try another one. Let's say we have x to the third minus 125. Well, once again, x to the third is on our list, and the number 125 is also on our list, except now we are subtracting them. So once again, I want to think about what would I have to cube to get x to the third power? And of course, that would be x. Minus, what would I have to cube to get the number 125? And the answer is 5. So wherever I see in my formula a, I'm going to use the x. Wherever I see in my formula b, I'm going to use the number 5. So let's just recall the formula. The formula tells us we have a, same sign b, a squared, opposite sign ab, always positive b squared. And now let's plug things in. So instead of a minus b, let's do x minus 5. I now need to take x and square it, plus a times b would be 5x. Always positive. Now take b and square it, and we get 25. And that is your factored form completely. Okay? Let's just try one more, one that's a bit more challenging. Let's say we have the following. Let's try maybe an 8x to the 6th minus, let's say, the number 125 y to the 3rd. Once again, we want to factor this completely. Think about what would you have to cube to get an 8x to the 6th power? Well, I would have to cube the number 2, and I would have to cube an x squared. Okay? Minus, and then I want to do the same thing with the 125y to the 3rd. What would I have to cube to get the number 125? The number 5. What would I have to cube to get y to the 3rd power? But the variable y. Let's recall now, 2x squared is going to be my a, 5y is going to act as the b. And if we follow the formula of a minus b times a squared plus ab plus b squared, now we plug in our quantities for a and b into the formula. So a is the 2x squared minus b is the 5y. Now I need to take a and square it. If you take 2x squared and square it, you would get a 4x squared. The next sign is going to be the opposite, so it's plus. Now I have to take a times b. If I take a 2x squared and multiply it with the 5y, that would give us a 10x squared y. Plus, always positive there. Finally, we have to take b and square it. If you take 5y and square it, that would give you a 25y squared. And that would be the factored form of that particular polynomial. Okay? So sums and differences of cubes, there's a slightly different formula, so you want to be familiar with that formula. Okay? Once again, the a and the b themselves, they pretty much are the same. What changes are the signs in the formula. So remember the word SOAP. When it comes to the sums and differences of perfect squares, as we talked about up here, the difference of two perfect squares is factorable, whereas the sum of two perfect squares is prime. And I'm actually going to say it's prime over the real number system. Later on, maybe when you take pre-calculus, you will learn about how you can factor over the imaginary number system. Okay? That completes section 7.3. And that actually completes all the different types of factoring that you're going to have to look for when you are looking to factor down polynomials. Okay? So there are now a total of 6 steps that you want to take a look at when factoring the polynomials. Descending order, leading coefficient positive. You want to look to see if there's a greatest common factor. Then you want to take a look at the number of terms. 4 terms, you use grouping. If we have trinomials, I gave you some skills for that. And then finally, what we have here are the factoring of these binomials, perfect cubes as well as perfect squares. All right, try the homework that goes along with this particular section. And as always, email me any questions. Until the next time, be well.